are going to do tonight to finish it. This type of factoring would be very useful if you want to take any other courses, especially calculus. Okay, so remind you this example again. Okay, again, I give you one factor and we find the others. So what we would like to do is we would like you to show that. Okay, we would like to show that x plus 5 is a factor. Okay, it's going to be a factor of this polynomial function f of x equal to f of x equal to the x cubed plus 6x squared, okay, minus x minus 30. And then we would like to get the help to give a complete factorization. And then write a complete factorization. A complete factorization of f of x. Okay, so that's the idea. So one factor is given. You want to find the other one. Okay, now you know what to do. We are going to use the syntactic method to confirm the factoring and at the same time find the reduced polynomials. So we talk about this is x plus 5. So if you read it equal to the 0, the root would be negative 5. So we are going to start with the dividing. So the solution is going to be, so you have a negative 5 into, bring the coefficient of the polynomial. We check that everything is all right. The third, the second, the first, and the constant. So the coefficient is going to be 1, 6, negative 1, negative 30. Syntactic method. You bring the 1 down, remember, and then you start multiplying. Negative 5 times 1 would be negative 5. So the leftover would be 1. Negative 5 times 1 would be negative 5. Okay, the leftover is going to be negative 6. We divide, we add. And the negative 5 times negative 6 would be a positive 30. So in that case, this is going to be your 0. Okay, so it's divisible because the remainder is equal to the 0. And the reduced polynomials, remember the reduced polynomials is going to be, we start with the x cubed. So the reduced one, the power would be 1 down. So it's going to be 1x squared plus x minus 6. That is going to be your reduced polynomials. So what we did, we get the confirmation that x plus 5 is a factor. Okay, x plus 5 is a factor. And in fact, we can factor it. So what we have is that your f of x is going to be this factor, which is x plus 5 times your reduced one. The reduced one is x squared plus x minus 6, which is easy to factor. Any question? Give us the numbers. What are we going to factor? How are we going to factor this one? Any suggestion? X squared plus x minus 6.
It's going to be 3 and negative 2.
So x plus 5, very good, times x plus 3 times x minus 2. That's it. So we get a complete factorization of the polynomial. Okay, any question? So you know that eventually we are interested in solving the equation or finding the zeros. So if we let this one to be equal to the 0, so what we can do is we can nicely, we have 3 factors, 3 zeros, and then we are done. Okay, any question? No. The plan is going to be, why not? Can we find out this factor ourselves? Okay, so if we can find this factor or these numbers, the zeros, you see the zeros of the function, if you let it equal to the 0, if you let it equal to the 0, so the zeros of the function would be what? X equal to the negative 5, okay, x equal to the negative 3, and x equal to 2. So these are going to be your 3 zeros of the function of the function, a polynomial that you get over here. So the question is, if we can guess one of them, then we can get the other ones. So the theorem that we are going to tell you that this solution must satisfy one condition. You see this condition over here going back? Look at these numbers. This is a polynomial. The leading term is 1. The leading term is 1, the coefficient of the x cubed. And the constant term is negative 30. Constant term is negative 30. If you consider the divisors of the 30 is divisible by what? Is divisible by, okay, 1, 2, 3, 5, 6, 10, 30. So if you are going to have a solution over here, you see these solutions must cover those divisors. So you have a negative 5, negative 3, and 2. All of them are dividing the 30 in this case. Of course, the coefficient over here is 1. So that is not surprising, because there is a theorem that will tell you this one. Okay, so the theorem will tell you that there is a connection. There is a connection between these zeros that we got over here. Okay, zeros that we got over here, and the divisors of these coefficients. You see, this coefficient is 1. We are going to bring this one into our argument too. And so this theorem that I'm going to talk about is going to be called rational zero theorem. So that gives you the candidate for the zeros of the polynomial, not all of them, just the candidate. So that would be good for us if you can guess what is the possible result is, and then we go for it, okay? So I'm going to give you the theorem. It's a great theorem in mathematics, okay? And then we come back and we do it ourselves, okay? We guess what's going to be the first one. Okay, any question? So what's the plan? The plan is how we're going to find this first factor. If I find the first factor, I reduce it, I should be able to do all of them. So this great theorem is given to you. That will take us, of course, to the next section. It's given to you in section 3.4, but we do it all together. Okay, so just remind you that we are in 3.4. There are quite a lot in this section, but we're going to take what we need and what's going to be connected to the argument that we're going to have. So the theorem is going to be called the rational, okay, the rational zero theorem. Zero theorem. We call it rational because the solution is a rational number. Remember, a rational number is a ratio of two integers. This means this theorem cannot be applied, if the solution is not going to be rational. Okay, so I write it down in the general form, then we go for it. Okay, great theorem. There are many applications of this one, extension in mathematics all over the places. Okay, if you continue taking courses in mathematics in future, you will see this theorem over and over and over. Okay, there you are. So we want to find the connection. The connection is if a polynomial is given to you. Let's write a polynomial in a general form. If f of x is going to be equal to, that they start with the highest power of n, and the coefficient we call it an, x to the n, okay, 5x to the 4th, that's the one. Then we keep going down, a standard form. The standard form, we go to the lower power, so we are going to use something like, we call it an minus 1, the next coefficient, and this is going to be x to the n minus 1. Okay, you start with the fifth power, you go to the 4th, and we continue. Okay, we continue that. So what we do is eventually you may get to the a1x, and then at the end a0. We are interested in the first coefficient and the last one, the leading one and the 0. Okay, so if this is going to be a polynomial, okay, if this is going to be a polynomial function, a polynomial function where this coefficient must be rational numbers only. Okay, so this coefficient must be integers, to start with, where a0, you see a0, a1, etc. to the an are going to be integers. Okay, are going to be integers, and you know that this is the the an is not equal to 0. These are the conditions that we impose to say that this polynomial is of degree n. But basically, it's going to be a polynomial, okay, of the n degree, where the coefficient of these polynomials are all integers. Okay, you cannot have radical coefficients, for example, to get this theorem. Now, what's the theorem? The theorem is going to be if you have one of the solution, if x equal to, okay, it's one of the solution, it's going to be a rational number. I'm going to call it p over q. Okay, p over q, 1/2, 1/5, 2, 3, 4, 5. Okay, because any integer can be written as a rational number. Okay, if x equal to the p over q is a rational solution, a rational zero of f of x. So if it's given to you, if you have it, then you see, then this p on the top, must be a divisor of the a0. Okay, divisor or a factor of the a0. Then p is a factor or a divisors. Okay, a factor of it or a divisors of a0, the constant term. Okay, that's it, a0, constant, just to remind you, constant term. That is going to be the p, okay, and the q, and the q is going to be a divisors of the leading term, an over here. Okay, and the q is a factor, okay, a factor or a divisors of an. What is an? Leading term. Okay, leading term of the polynomial. Okay, so that will give you a hint that if you do have a solution, if your solution is going to be a rational number, the top of the fraction must be a divisors of the constant term, a0, and the bottom of the fraction must be a divisors of an. Okay? Remember, this theorem is not telling you that this is a solution. No, the converse is not going to be true. So this means if you want to find the possibilities of the rational solution of your polynomials, you should check these type of numbers. Okay, these type of numbers. Okay, so what we can do is we can form these possibilities, and then we check to see if we can get somewhere. Okay, so any question? I'm going to give you an example to clarify it because you're not going to prove it. So this just make sure you understand what we are talking about. This will tell you that if this is a solution, is a solution. If it's going to be a solution, must satisfy this condition. The top must be factors of the a0, and the bottom must be a factor of the an. Okay, so what we are going to do is, if you be given a polynomial, you check these possibilities. Then you can use that factor theorem that we talk about it to find out if you are lucky to get one of the solutions right away. Okay, so I'm going to give an example to clarify it to what's going on for this theorem. Okay, any question? So let's see how we're going to apply it. Okay, so what we are going to do is an equation would be given, and we want to find the see, this is it, example. Let's start with this one. We want to find all zeros, find all it's going to be all rational zeros, but we call it all zeros. Okay, you want to find all zeros or rational zeros of the function, of this function. The function is f of x equal to the x to the third. Okay, it's x to the third plus 5x squared 5x squared plus 2x plus 2x minus 8. You see, that's the one. Eventually, this is going to be equal to the 0, and you're going to find the solutions. Remember, we need one factors, one solution. If you can guess one of the solutions, then we can use the syntactic method to reduce it into the quadratic, and then we go for it. Now we are going to use this theorem to find the possibilities. Okay, how are we going to find the possibilities? This is it. Identify the constant term solution. You see the constant term A0 is equal to the -8. That's the constant term. Leading term, leading coefficient over here, you see AN. AN is equal to the 1. Okay, so bring that P over Q that we talk about it. You see the possibilities. The possibility is what? The possibility is X. This X is going to be P over Q. P over Q. What is P? P are the factors of the -8. Okay, I just remind you that these are going to be divisors. Okay, these are going to be divisors or factors of A0, and this is going to be factors of AN. Okay, factors of the A0. A0 is -8. 8 is divisible by what? It's divisible by 1, 2, 4, 8. So the possibility for the top, you see the possibility for the top are going to be positive -1, positive -2, positive -4, and positive -8. These are the divisors of the constant term. Okay, any question? You have to consider either both positive and the negative one. Now the bottom one is going to be divisors of the leading term, AN. Divisors of 1 is just positive -1, positive -1. Okay, now divide. You divide, each from the top by the bottom. The bottom is just 1. So what's going to be the possibility over here? You see the possibility are going to be, you divide. So the possibility is going to be positive -1, positive -2, positive -4. Okay, this is it, positive -4 and positive -8. So these are going to be the candidates. Okay, the candidates for the zeros of these polynomials. So what I'm going to do is we are going to check if they are going to be, the zeros. You know that they are going to be zeros if you can use syntactic method to check it, to check these numbers. When you are going to be in calculus on any courses, when they give you these equations, okay, sometimes it's nice to check. You know that we can check it by substituting into the function, or we can use the syntactic method. Since we are interested in the leftover, so you better use syntactic method, okay? If you are not going to be interested in leftover, you can substitute. But one hint that would be useful for most of the problem in calculus or, in any other courses, you just check the sum of the coefficient. I talked about it the other night. You see sum of the coefficient, 1, 5, 2, 8. If you add them together, 1 and 5 would be 6, 6 and 2 would be 8, 8 and 8 would cancel out. So we talk about it. If sum of the coefficients happen to be equal to the 0, x equal to 1 is one of the solution. So that would be very helpful. And the 1 is here. So you better check the syntactic method for x equal to 1 first. Quickly that reduce into the second, and then you'll be able to do it. Okay, it's not the case all the time, but most of the time that's the case. So why not check this one first? Okay, check this one would be very, very helpful. Any question? Because you have to check quite a lot of numbers here, okay? So if this is given to you, you are lucky. So check this one. In this case, that's true. So I guess that I should check 1 first, okay? I should check the 1 first. You know that this is it. This is 1. Bring the coefficient of your polynomials. What you have the 1 and the 5 and the 2 and the -8. Okay, you bring the 1 down and start multiplying. If you multiply 1 times 1 would be 5. 1, that give you 6. 1 times 6 would be 6, make it into the 8, and that give you 8 and 0. Okay, we know that. We must get the 0 over here. So this means x minus 1 is a factor. Remember, x equal to 1 is the solution. So this means x minus 1 is a factor, and we already got the reduced, okay, this is going to be a reduced polynomials. Okay, so x minus 1 is a factor. X minus 1 is a factor. Okay, and I can get the other one. Any question? I have to go to the next page. Are you done? So the leftover, this is 1, 6, 8. So the reduced polynomials, you see reduced polynomial is going to be 1x squared plus 6x plus 8, which is easy to factor. So I go to the next page and continue. So I do have one of the solutions and one of the factors. So what we have so far, so far f of x is going to be x minus 1 times the leftover. Okay, that we got over here, it was x squared. Okay, x squared plus 6x plus 8. You see the leftover is very easy. We don't need anything else. Okay, we don't need anything else and we can factor it easily. Give us the numbers. To factoring x squared plus 6x plus 8. Any suggestion?
4 and 2.
Very good. 4 and 2 is going to be x minus 1, x plus 4 times x plus 2. That's it. You see, when we didn't need to, to check any other numbers from the list that we have. So that's it. So this will tell us that what is going to be the zeros. If you put it equal to the zeros, so the zeros are going to be x equal to 1, x equal to the negative 4, and x equal to the negative 2. And we are done. Okay, so that's going to be type 1 of this type of the equation. Okay, any question? So it's important to find the first one. As soon as you find the first one, then you'll be able to go on and get the other ones. Okay, I'm going to give another one. Any question? So it's very, very easy method. So useful in future. Okay, so let's have another one, the other example, to see what is going to be different conditions that we are going to have. Okay, let's check this one first. We want to find all zeros, find all rational zeros, if you like, zeros of this polynomial. Okay, this is it. F of x equal to the 2x cubed. Okay, 2x cubed minus 11x squared, and that is going to be 10x. Okay, 10x plus 8. Just having various coefficients in this case. Okay, now you know how to do it. Solution. So identify the constant term, which is going to be equal to the 8. That's a constant term. Then the leading term, an equal to 2. Okay, get the possibilities. The possibilities, x equal to the p over q. Remember, p is the factors of, okay, it's the factors of a0. Just write it down, just to remind you. This is going to be factors of an. So we have the a0 again. The factors are going to be 1, 2. So it's going to be positive negative 1, positive negative 2, positive negative 4, and the positive negative 8. Then the possibility for an is divisible by 1 and 2. So positive negative 1 and the positive negative 2. Okay, so get the possibilities. So x is equal to the possibility. You have to divide everything on the top by each member over here. If you divide everything by 1, so you get positive negative 1, positive negative 2. okay, positive negative 4, positive negative 8 to start with. Then you have to go back. You go back and divide everything by 2. Okay, every members by 2. So the first one give you positive negative 1/2. Okay, the second one, 2 divided by 2 would be 1. We already got it. 4 divided by 2 would be 2. We got it. And 8 divided by 4 is 4. We have all the possibilities. Okay, so these are going to be the possibilities. Any question? Now we have to try. We have to try to see if we can get the first one. A possibility for 1 and negative 1. Okay, for 1, if you check, you are not going to get anything this time because the coefficient is 2 minus 11 plus 10. 8 would be 18. It's not going to be 0. So x equal to 1 is not going to be one of your solution. Okay, you can check, I check one of them so that you will see that negative 1 is not the solution. Okay, so if you check, 2 is going to be, I can check 2 because, I don't know. You have to check, to get one of them. So if you check 2, so 2 into, okay, between the coefficient is going to be 2 minus 11, okay, and this is going to be the 10 and the 8. And so we are going to bring it down. This is going to be 2 down, and then we continue. 2 times 2 would be 4. Okay, that gives negative 7. So that gives negative 14. Negative 14, that gives us a negative 4. And this is going to be negative 8 and done. Any question? So, I checked it before, so I just don't to spend more time on it. Okay, so it's divisible, and the remainder over here is going to be what? It's going to be 2. We start with the cube, so it's going to be 2x squared. Okay, 2x squared minus 7x minus 4. That is going to be your leftover. So, so far we understand that x minus 2 is a factor. Okay, it's going to be a factor. It's going to be a factor and the leftover. Okay, so this is it. It's going to be f of x equal to the x minus 2 times 2x squared minus 7x minus 4. Okay, then you have to continue with this one. You can factor it. Since they ask for the zeros, even you can let it equal to the 0. Use quadratic formula. See, if you feel uncomfortable. If you feel uncomfortable, to do the factoring, you just let it equal to the 0. Sometimes you may have to. But in this case, it's okay. It's not going to be difficult to factor. Or you can check some of these numbers that you already got over there. So the usual factoring give us the result. Okay, x minus 2. This is going to be, in fact, we get the x. Okay, this is it. It's going to be x minus 4, and this is going to be 2x plus 1. Okay, this is going to be x minus 2, x minus 4 times 2x plus 1. You know that 2x times x would be 2x squared, and you get everything, in order right away. Again, if you feel uncomfortable, you can let it equal to the 0 and use quadratic formula to get the result. But these are unusual factoring that we are going to do. Okay, any question? So these two was nice, okay, to get the result. Let's see what is going to be some other difficulty that we're going to have. Remember, if it was an equation, as I told you, you can use quadratic formula to factor this one. So I'm going to give you another one, but I changed the direction of the instruction, the type that you may see in future. Any question? So guess one of them. If you're lucky, you may see it right away. Otherwise, you may spend some time to find it. Now, the cases that are going to be a little bit different. It's not the case that always you will get it, okay? Look at this one. This is the type that you're going to use in future. You may be asked, find all solutions, okay? You may ask to find, okay, all zeros, or solutions. Okay, all zeros or solutions of this equation, of the equation. So what is going to be this equation? The equation is 3x cubed. Okay, there's going to be 3x cubed plus 4x squared. Okay, 4x squared minus 7x plus 2 equal to the 0. Let's see what is special about this one. Okay, to get this number. Again, you know, if it's going to be given to you, you may use grouping method in general, of course. We can't do it. Okay, sometimes we'll be able to do by grouping method. So we are going to use the method that we talk about it. Okay, are you ready? Check the possibilities. We do it quickly now that we get the idea. You see the A0 is equal to 2, AN is equal to 3. Possibilities, X equal to the PQ. Okay, we talk about that P is the divisors of the A0, and the divisors are positive negative 1. Okay, and the positive negative 2, that's the A0. And the bottom one is the possibility divisors of the 3, which are going to be positive negative 1 and the positive negative 3. Any question? So on the top is always the divisors of the 2, and on the bottom is going to be divisors of the Q. So if you divide, so the possibility that we can have, we divide the top by 1, so we get positive negative 1. Okay, positive negative 1, and over here we get a positive negative 2. Okay, positive negative 2. And then if you divide by 3, if you divide by 3, that gives you what? You already got the 1. Okay, so we got the positive negative 1/3. Okay, and we get the positive negative 2/3. So these are going to be the possible candidates for your rational solutions. Okay, to get these numbers. So you may try numbers to see if you can get one of these. Okay, you cannot, you just check the 1 is not going to be a good one because the sum of the coefficients is not 0. Okay, even negative 1 is not going to be good. Even we can check the 2 if you like. You know, I just check the 2 for you. You see, if you check the 2, so it's going to be 2 into what? Into a 3, 4, negative 7, and 2. Okay, you bring the 3 down, and you investigate. Okay, if you investigate, 2 times 3 would be 6, and that gives you 10. Okay, 2 times 10 would be 20, and that gives you 13, and 2 times 13 would be 26. Okay, which is no good. Okay, this is not good. Even negative 2 is not going to be good. You can check it for yourself. You see, if you get negative 2, you can check the negative 2 for yourself. It's no good. Okay, 1 and negative 1 is not going to be good at all. Okay, you can check them. X equal to positive negative 1. You won't get anything. Okay, so you may try one of these. Okay, you may try one of these fractions. You may try the 1/3 or the 2/3. Okay, so how about 2/3? If you check X equal to the 2/3, okay, if you check the 2/3 to see if it's going to be the case, 2/3, and the numbers that we have, it's a 3, 4, negative 7, and 2. Okay, I bring the 3 down, and I multiply it. So if you multiply 2/3 times 3, 2/3 times 3 would be 2. So that gives you 2, which is going to be 6. Okay, 2/3 times 6, 6 times 2 would be 12/3. 12/3 is 4. So that gives you negative 3. Okay, 2/3 times negative 3 would be negative 6 over 3, which is going to be a negative 2. So we get a 0 here. Okay, so this means x minus 2/3 is going to be a factor, or x minus x equal to 2/3 is one of the solutions. Okay, and the leftover, look at the leftover. The leftover would be 3x squared plus 6x, okay, minus 3. So this means x equal to 2 is a solution, or x minus 2/3 is a factor. Doesn't matter. Okay, x minus 2/3 is going to be a factor. Is going to be a factor, and what we have the fact that the f of x is equal to the x minus 2/3 times the leftover, which is a 3x squared plus 6x minus 3. Any question? I just wanted to see the difficulty, or the importance of this theorem. So far we got 2/3 as one of the solution. We need 2 more because this is a squared. Okay, so what we can do is, for the other problems it was easy to factor, but not this one, not this one. And you don't have any more numbers to check. You see, these numbers are out, all of them. When you didn't get it for the other ones, you cannot get it for here. Okay, so this is the time that we go to the old-fashioned way to do it. This is it. You want to find the solution of this equation. So this is it. We have the 3x squared. Okay, 3x squared plus 6x minus 3 equal to the 0. You have no other choice than to try to solve this equation. Okay, you know that there is a factor 3. You can put out the 3 here, or you can divide by 3 if you like. Okay, if you divide by 3, so the leftover is going to be x squared plus 2x minus 1 equal to the 0. Any question? If you divide it, that is make it easier to handle it. You cannot factor it because you already check. Okay, so quadratic formula. Okay, quadratic formula, whatever version you like. The version that I like is I just check first. I check the discriminant to see if there is any solution. Okay, so this is it. A is equal to 1. B is equal to 2. My C is equal to the negative 1. So I check the B squared minus 4AC to get an idea of what's going on. B squared minus 4AC. Okay, substitute. If you substitute, what's going to be the result? It's going to be 2 squared minus 4 times AC, 1 times a negative 1. So that gives you 4. Okay, that gives you 4 plus 4 is 8. It's not a perfect square. It's nice. It's positive. Okay, so I got the delta equal to the 8. Now I'm ready to get the solution of the equation. Okay, any question? So be ready for it. Okay, you reduce it into the square, that's enough for you. You'll be able to do it. Okay, so we use the quadratic formula to get the final answer. I put it over here so that I have everything here so we can see it, compare them together. Okay, so I'm going to use quadratic formula for this one. So what is going to be x is equal to a negative b plus or minus a radical delta over 2a, the quadratic formula. So it's going to be equal to negative b. What's a b? B is a 2, so it's going to be negative 2 plus or minus radical 8 divided by 2a. 2a, a is 1. So the top give me negative 2. You know that the radical 8 is 2 radical 2. So that gives you positive negative 2 radical 2 divided by 2. Okay, now we can factor out and simplify all the 2's. So the result is going to be negative 1 plus or minus radical 2. Okay, so there you are. That is the reason that you didn't get this one. Remember, that theorem is called rational zero theorem. Rational zero theorem means that give you only, okay, you can discuss only the rational solutions. This is irrational. Negative 1 plus or minus radical 2. That's why you didn't get it here. Okay, you didn't get it here. So you got to be careful. You are going to get the rational solutions. So you may get over here. This is okay. It's not the rational numbers. That's why you didn't get it. So be ready for it. Be ready for it, and you should be okay, thankful that you'll be able to find one of the solutions. Okay, you reduce it at least into the quadratic one to be able to take care of it. Okay, you have a couple of them in your book, in your assignment. So don't be surprised when you get it to the quadratic one. Then you'll be able to take care of that quadratic, and then you'll be fine. Okay, any question?
Yeah.
So easy method. Yes.
What happened to the 3? What do you do with the 3 that you factor out?
You see 3 is a constant. 3 is never 0.
Oh, okay.
I divide, I divide by 3 over here. So I divided by 3. So I left with the x squared plus 2x minus 1. I divide both sides by 3. If you factor it, you know that 3 is never 0. So you have to check these zeros, x squared plus 2x minus 1. Okay, any question? So when we get to the application really in future, you may have these type of problems more than the other one that I did. Okay, so you got to be patient. You got to be patient, and that's it. As soon as you find one of the solution, that would be good for you. Then you don't have to you don't have to factor it anymore. So this is most of the time for the cubic one. I give you one with the 4th degree, and one that there is a possibility that when you going down reducing, you see, look at the term that I told you. I didn't say that find all the rational solution of the equation. I said find all solutions of the equations. Or we ask you find all real solutions. So that's a hint, because I didn't get all the rational solutions, okay? Because these are irrational. Because 1 plus radical 2, you cannot find it. So that is the difference when we express it. You may have something to the 4th. It's not a big deal, but takes a little bit more time. I just quickly give you one. And you may get, you see this one that I did? This quadratic, I solve it, I get what I got over here, I got the rational solutions. You may solve it and you have to use complex numbers, okay? It depends if you are going to be in the domain that will let you use complex numbers, okay? So it depends where you are. If you are in calculus, you are not going to use it, because over there, for your calculus 1, 2, 3 that you read, you are not going to use, the function with the complex domain. It's out of question. But if you continue taking other courses, then you may need that one. Or you measure in physics, you go with the calculus 1, 2, 3, then you come back. So, but we have to give you one example, but we are not going to go through the details. We are not going to be much interested, depends on the direction of your courses in future. Okay, that's why I just give you a quick one. But I'd like to give you quickly one with the 4th degree, because you have a couple of them in your book. So we may question you that. Any question? Nice method, okay? Nice method, you see, you get this one. So let's give one with the 4th degree, and at the end, I give you one with the complex. And there are some other things that you can summarize, simplify these methods, but you don't need it really. It doesn't worth it at this level. It's good, but these operations are limited, cubic or the 4th degree. So be able to get through one of these, and that would be enough for us for the college algebra. Okay, so one with the 4th degree, a little bit more, and then one with the complex numbers, and be done. So this is it, this example, and you should expect all these 4 types for next test. So this is it, we wanted to find. You see, look at the expressions, find all real solutions. Real solutions of the equation. That's it. This is the equation that we're going to be interested in. 2x to the 4th plus x cubed plus x cubed minus 24x squared plus 20x plus 16 equal to the 0. See, that's it. Equation of the 4th degree. So we expect to have 4 solutions. Okay, let's see if we can find one of them. If you find one, you reduce it into the 3rd. Then you need find another one from the cubic to change it to the square, and eventually you'll be able to solve it. Okay, are you ready? That's it. The plan. Possibilities. Okay, possibility, the constant term is 16. Okay, A0 is equal to the 16, and the leading term is 2. Okay, you have quite a lot of possibilities. So what is the possibilities? X equal to the PQ. The P divisors of A0, 16, quite a lot of numbers. Okay, 16 is divisible by 1, positive negative 1, divisible by 2, positive negative 2, divisible by 4, divisible by 8, and divisible by 16. Okay, on the top, you must get the factors or the divisors of 16. Okay, down the bottom, you get the divisibility by 2. 2 is going to be positive negative 1 and the positive negative 2. Okay, these are the factors. Divide all the top by the any of the bottom. So x is going to be equal to, when you divide by 1, you just repeat it. So it's going to be positive negative 1. Okay, so we get a positive negative 1, positive negative 2. Okay, positive negative 4, positive negative 8, positive negative 16. When you divide all of them by 1, then you have to divide all of them by 2. Okay, if you divide the first one by 2, that gives you 1/2, which is new, positive negative 1/2. If you divide the second one by 2, you see 2 by 2 would be 1. We already got it. 4 by 2 would be 2. We already got it. 8 by 2 is 4, and the 16 by 2 is 8. So we are not going to get anything new. Any question? So identify the divisors and then divide all of them by each one here. All of them by each one here. And there are going to be some repetition that we are not going to repeat it. There you are. These are the candidates. Okay, these are going to be the candidates. So we check to see if you can get one of them. Okay, you can try to see this is going to be the case. You see 1 and negative 1 would be out. You cannot find it. Okay, you can quickly check that the 1 would be out. I just check one of them for you. I don't have time. This is going to be, but you have to check it yourself. Okay, if you check the 1, this is going to be 2, 1. The sum of coefficients are not 0 really. So even you don't have to check it, but I just check it to see it. Okay, we bring the 2 down, to get the idea. So 1 times 2 would be 2, which is 3. So that give you a 3, which is going to be negative 21. So this is a negative 21, which is a negative 1. And so 15, you're not going to get it. Okay, so x equal to 1 is out. Similarly, if you check x equal to negative 1 would be out. Okay, so the next number first. So I'm going to check 2. Any question? We have no other choice. We have to check to see. So I'm going to check 2. Okay, if you check 2, so that's going to be a 2, 1, negative 24, 20, and 16. Okay, so we bring the 2 down, and then we are going to continue. So 2 times 2 would be 4, make it into the 5. 2 times 5 would be 10. So we get the negative 14. 2 times 14, 28. So that gives a negative 8. And that's going to be negative 16 and the 0. Nice. Okay. So we get the first factor that we need. But this is the 4th degree polynomials. So it's not going to be enough. So what's going to be the leftover? You see, this is going to be a leftover. Remember, we start with the 4th power. So this is going to be the 3rd. So we get a 2x cubed plus 5x squared minus 14x minus 8. And we already got, that x equal to 2 is one of your solutions. Any question? That's a reduced polynomial. You're going to work on this one. Because so far, x minus 2 is a factor. You see, so far, this is what you have so far. you have the fact that your f of x is going to be x minus 2 times 2x cubed 5x squared minus 14x minus 8. Okay, but you have to focus on this one. Okay, focus on this one and continue. Try for more numbers. Okay, try more numbers again. But you see, these numbers that you check, these numbers, even x equal to 2, it may be a repeated one. The one that you disqualify, you're not going to repeat it again because you don't need it. If it's going to be a factor, it's already got it. So check the other numbers, the leftovers. So in this one, the 2 would be a repeated one. If you check the 2 again, you have to check it. Maybe, it's going to be a repeated solution. And so we check the 2 again to see if this is going to be the case. So the coefficients are 2, 5. I just wanted to see that there may be a repeated solution. That's it. So we bring the 2 down. We bring the 2 down and we repeat. 2 times 2 would be 4. Okay, would be 4, so that make it to the 9. 2 times 9 would be 18. You make it to the 4, and this is going to be 8, 0. You see? So this means x equal to 2 is a repeated solution. A repeated factor. You can have x minus 2 times x minus 2 times x minus 2 forever. Okay, so we check it. And now the leftover is going to be a quadratic one that can be handled. Okay, so it's going to be 2x squared plus 9x plus 4. Any question? So we get one more factor. So the f of x is going to be equal to, we have the x minus 2, we have the x minus 2, and then we have 2x squared plus 9x plus 4. You have various possibility. You can factor it. You can use one of those numbers, or you can let it equal to the 0 and use quadratic formula. But it's easy to factor, but you have those options. So if you factor it, that should give you, this is a 2, so it's going to be 2x. Okay, it's going to be 2x plus 1 times x plus 4. You can try the numbers that you have over here to check, or let it equal to the 0. Okay, use quadratic formula to get the solutions. So the solution of that equation is equal to, if you let this one equal to the 0, so the solutions would be x equal to the 2, x equal to 2, okay, x equal to the negative 4, and x equal to the negative half. And of course, all of them are on the list that we talk about it. Okay, so again, it's not difficult. It's not a big deal really. Eventually we get it. But
would you have to list the x equal to 2 twice?
We just show that it's repeated solution.
Okay.
Yes, because because you need to have 4 solutions over here. Okay. So that's why we write it down to show that we did get 4 solutions, but one of them is repeated one. Okay, any question? So that is going to be when we get to the 4th. The only other one is going to be the case that quadratic one that we get right at the end, you may get a very mild complex one. Okay, we can argue about the complex numbers and the complex solution, but the cases that you are going to use at this level are not going to be complicated. So that's why, and in your book, they just give you a couple of examples. So that's why I focus on giving you one examples rather than talking about the property of the complex solutions. Okay, so this is the last type of the example that we have. So we may ask you just, this is it, find again all solutions. All solutions of the equation. Okay, they may say all solution real or complex. For this one, real or complex. That's the hint. this means you may get a complex solution, so bring it in. If you say only find all real solutions, so you're not going to consider the complex. Find all solution, real or complex, of this equation. Okay, the equation is, I think this would give you one complex. And this is it, 3x squared. Again, a very mild one, because we don't have many property of the complex numbers at the college algebra level. Okay, there you are. It's cubed. You need one solution. Okay, guess one and then reduce it to the square, and then you'll be able to do it. Are you ready? Solution. Let's see what is special about this one. Constant term -5. Okay, leading term 1. Check the possibilities. Not match. In this case, it's going to be x equal to, okay, x equal to the p over q. P divisors of a 0. 5 is a number, a prime number. So it's going to be positive -1 and the positive -5. Okay, that's it. The constant term is just a positive -1. Okay, and this is it. So if you divide, x would be what? It's going to be just positive -1 and the positive -5. Okay, you have the 1 and the -1. Quickly check the sum of the coefficient. You see sum of the coefficient, 1 and 7 would be 8. -5 and -3 would be 0 right away. If it's going to be in calculus, we check this one right away and we go on. But we want to check the theorem here. So check x equal to 1. You need the leftover, so you have to do it. 1 minus 3, 7 and -5. Okay, bring the 1 down. 1 down, multiply. 1 times 1 would be 1. So that gives us a -2. 1 times -2 would be a -2. That gives us a 5. Okay, 1 times 5 would be 5. We get the 0. Nice. So x equal to 1 is one of the solutions. So we have to use it to factor it. Okay, so x minus 1 is a factor. So f of x would be what? Would be x minus 1 times the leftover reduced polynomial. What's a reduced polynomial? It's x squared minus 2x plus 5. Okay, so it's going to be x squared minus 2x plus 5. Any question? Now, we have to work on this one. You see, x squared minus 2x plus 5. You cannot factor it because you need two numbers with the product of 5, okay, and the sum of 2, which is not possible. So this is not going to be helpful. Okay, this means there must be other type of the solutions, okay? Because if it was a rational solution, the possibility is it may be here or it must be here. Okay, so that is why you are going to take this one out and you go to the quadratic equation. Any question? So we check the possibility for the rational 0. We got 1, but there is no possibility for the other one. So we check, we may have an irrational solution or we may have a complex solution. So I'm going to test it to see what type of solution I'm going to have. It's going to be a equal to the 1, b equal to the -2, and the c equal to the 5. I check the discriminant, okay, b squared minus 4ac. So the b squared would be -2. Okay, that's a -2 squared minus 4ac. 1 times 5. Okay, so that give you what? That give you 4 minus 20, which is -16. So the delta is -16. You know that. When it's a negative, you are going to have a complex solution. There is no real solution. Since they tell you that find all solutions, real or complex, you have to continue. Okay, so you just identify that there is no real solution. Okay, but we go on. we provide the formula negative b plus or minus radical delta over 2a, okay, to check the possibilities or to check the solution. Negative b is a negative 2, so negative 2 plus or minus radical, okay, negative 16 over 2a, which is 2 times 1. You know that radical negative 16, we change it to the 4i, and then we take care of it. So it's going to be x equal to, it's a 2 plus or minus, okay, 4i. And this is going to be 2. You divide by 2, it's going to be 2 over 2 plus or minus 4 half over I. You simplify it, x would be 1 plus or minus 2i. That's it. So the solutions are going to be, we get one real solution, 1, and the other solutions are, you know that the complex solutions are going to be coming in pairs. So we get the 3 solutions. Okay, so don't be surprised. You may get a rational solution as I did the other one for you, 1 possibly get radical 2, or you may get a very mild complex solutions at the end. But that's it. We get the first factor and you'll be able to do it. Any question? I can give a break now. You got 10 minutes. Okay, it's 8, 20, 23. 10 minutes, we come back. We are going to give you an introduction of the, we work on the next chapter. We work on the rational functions, which is very important one. So we try to give you some introduction of that one too. Okay, so we are done with the polynomials. We talk about the graph of the polynomials. Remember those end behaviors, graphing. We talk about the factoring polynomials. This is going to be solutions and the, okay, some idea of the rational zeros. So see you in 10 minutes to get the numbers. Okay, any question? So we are going to be done with these polynomials and anything in this chapter. So we are going to look at the chapter 4, mainly rational functions. Very important one again. Give you some idea of what's going on with this type of function. We already have this function from time to time, but officially we didn't discuss the property of these functions, okay? So that will probably take us to the next test. Okay, so this is chapter 4.1.
It's
Rational.
like are you gonna need your own toothpaste when you go down to Borrego?
Sorry, it's a.
And we can just share until you get it, because I don't want to have like 2 toothpaste. If you wanted to get your own toothpaste, fine. I don't. No,
Hey,
I didn't.
mute yourself.
Okay, so this is it. We go to the chapter 4. So we take the 4.1, rational functions. Quite interesting, and many property. Again, if you want to take future courses, this is going to be a very important concept, and I expect you to know what we are going to talk about it. Okay, so it's 4.1. It's very dense section. Take us maybe tonight and the next week, and we give you 2-3 questions from this section on the next test. Okay, so pay attention and get practice on this one. So what is going to be rational functions? Rational functions. You know that in general we have rational numbers. Rational numbers is just a reminder. That would be good to get a better understanding of these type of functions. Okay, I just recall the rational number first. Recall that a rational number. Okay, a rational number is the ratio of 2 integers. Is the ratio, okay, of 2 integers. 2 integers. Integer is going to be a over b with one condition. With the condition that the denominator, this b, cannot be 0. So that's the definition of the rational numbers. Okay, so you know that something like 1/2, okay, 4/5, 3, 7 are rational numbers. Okay, this is the rational numbers. So we are going to define something for the functions. A rational function is a ratio of 2 polynomials. Okay, they are integers, those polynomials. So a rational function is the ratio, okay, the ratio of 2 polynomials. Okay, so f of x equal to, I know I put the top one, I call it n of x for the numerator, and I call this one d of x for the denominator. Okay, it's because there are some property that we are going to refer to it, so we're just using this one. Okay, so a rational function is a ratio of 2 polynomials. So this is going to be a rational function. Is a rational function where or when n of x and d of x are simply polynomials. So it means all the powers must be positive integers, no negative power. Okay, no radical. It's gonna be something nice all through. Okay. So the examples of these rational functions are going to be, so the following, okay, the following are going to be rational function. Just list the one that we are going to use. So these are going to be the possibilities. And the first one is just a very popular and easy one, f of x equal to 2x plus 1 over x minus 5. That's very popular in application. In various applications, they use this one. In physics, they call it bilinear transformation. And, they have some different phenomena, mathematical modeling with this function. That's why they like it. That is one model. And the other one is this one. There's something about this one that we are interested in and we want to emphasize. So that's why I call it a type 2. Okay, x minus 1 over x squared minus 1. And that is 1. And the number 3 is going to be h of x equal to, okay, this is going to be h of x equal to 3x plus 1. And this is going to be x squared plus 16. This is another type that we are going to be interested in. Okay. And the last type that we're going to see is this one, f of x equal to, say, x cubed. Okay, this is going to be x cubed. And this is going to be x squared minus 9. There are more, but we are not going to be interested in. I can write to one more. G of x equal to something like x squared plus 2x plus 7. And this is going to be x squared minus x minus 6. Okay, so as you can see, the top is a polynomial and the bottom one is a polynomial. So this is a rational function. So you cannot have something like x to the negative 2, negative 3. You know that. Because the polynomials, the powers are going to be just positive integers. Okay. Any question? First thing to do is the domain of this function. Okay, the domain of this function, the possibilities for the x. You know that in the case of the rational number, there was a restriction. You see, the restriction is the denominator cannot be equal to the 0. So since you're dealing with the x and x is a free agent, x can be any number. So you have to restrict the x. Restrict it so that this makes sense. You know that restriction is going to be, you are going to make sure that the denominator is not 0. So this denominator will do 0 at 5. So this function is defined everywhere except at 5. So you have to exclude the zeros of the denominators. So you let the denominator equal to the 0. Whatever number you got, you are going to throw it out. Okay? So that would be your first job, finding the domain of the rational function. I'm going to find the domain of all of these, just to give you an idea. Any question? We already done the domain, but we just, officially we didn't have it. So you are going to have one question on this one again. Whatever you want to do for the rational function, you have to give us the domain first. Okay, so the definition of the domain officially, and then this example. Okay, so domain of a rational function. And this is it, the definition. There you are. A rational function. A rational function. A rational function, f of x equal to n of x on the top and the d of x on the bottom is defined. Okay, it's going to be defined. It's going to be defined everywhere. Everywhere except, okay, when d of x is equal to the 0. Okay, so you have to exclude these numbers. Okay, so basically, so the domain of this function is going to be all x's for which d of x is not equal to the 0. They call it the set notation, but we are interested in interval notation for this one, remember. To get the domain, interval notation only. Because, you know, in future, whatever you want to do, you go with the interval notation rather than, this is set notation. Mathematically, it's not wrong, even if you give it us on the test, but we try to avoid it. Okay, so we check all the 4 types of function that we have for the domain, and this is how going to be questioned. Any question? Just keep going with this definition first to get to the some more involved terms, then we stop. Find the domain of each function. Domain of each function. All 4 types that I talk about it, we bring them in and we identify the domain. And the type 1 is just the one from physics. Okay, bilinear function, easy. F of x equal to 3x plus 2 and over x plus 3. Okay, so this is defined everywhere when the denominator is 0. Denominator is 0 at -3. So this is it. This is everywhere. But you have to take out the -3. Okay, so the domain is interval notation. Start from -infinity up to the -3, but the union with -3 and positive infinity. So that give you the domain and you're done. Any question? So get used to this type of notation, interval notation. Of course, this must be parentheses, okay? On the test, some people, they use bracket. You cannot use bracket because there is a hole here. If you use bracket, means you believe in it, but you don't want it. So that's why you have to exclude it. Any question? That's a type 1. Type 2. It's the one that some people, they miss it on the test. G of x equal to x minus 2, and this is x squared minus 4. That's the one. Okay, in order to get where the denominator is going to be 0, so you need to factor denominator, and that will cause some difficulty for some people. Okay, so if you factor it, so the g of x is going to be equal to x minus 2 on the top, and the x minus 2 times x plus 2 times the bottom. You see, some people, they simplify it, which is wrong. You have to find the domain first. Don't simplify it, okay? Because you have to have the domain. Then in the territory of the domain, in the domain, you can simplify it. You don't have the domain yet, okay? So don't simplify it. So what we're going to do is we are going to take out 2 points. The denominator would be 0 at 2 points. So we have to exclude the -2. And then we have to exclude the 2. Okay, now we get 1, 2, 3 portion. So the domain would be a -infinity up to the -2. Okay, union with -2 and +2. Union with 2 and positive infinity. So that would give you the domain of the function, okay? After the domain, you will see later on that we are going to simplify it. But first, we need the domain. Because, you know, when you simplify it, you divide by x minus 2. You have to make sure that x minus 2 is not 0. Okay? But when we get the domain, you see x is never equal to 2. So it's not 0. We can simplify it. But not before the domain. Okay? Make sure you know this one. And we are going to see it, you know, when we get to the graphing this function, we are going to do this one over and over. Okay, any question? So make sure don't miss it. There is a common factor, yes, but don't simplify it for this level. So that's going to be the case. The case 3 is that famous function. You see h of x equal to, you may be given x squared on the top and the x squared plus 25 down the bottom. You see this one? Denominator is x squared plus 25, okay, not minus 25. When it's x squared plus 25, you cannot factor it. You can factor it using complex numbers, but I told you, no complex numbers with the functions. So since we cannot factor it, you see, each factor give you 1 0. Remember those factorization one. So since you cannot factor it, this denominator is never 0. It's impossible to find a number value of the x that make this one 0. So nothing to worry about, you see. This is the number line. Since no factoring, so we are not going to do anything over here. Nice. So the domain is all real numbers, or negative infinity and positive infinity, or R. We accept both of them. Okay, the reason x squared plus 25 is not factorable, is prime. Is not factorable. Since it's not factorable, so you cannot simplify it. You cannot factor it. You cannot make it 0. Okay, any question? So these are the main 3 possibilities that we have. Just be careful, especially the middle one. Don't simplify it. Find the domain first to get these numbers. And the last one, you know, it's not factorable, and then you're done. Okay, any question? And sometimes they may give you something more. These are, because we want to get to the graph, these are mostly the one that we're going to have. But in case see something else is given to you, so we are ready for it. Okay, so that gives us a number 4. The number 4 is going to be something like f of x, okay, equal to f of x equal to the x plus 3. And then the denominator, they may give you something like x cubed minus x. You see, that's the one. You have it. You have 1 or 2 in your book. To find the domain, you have to factor the denominator. The denominator, you have to factor out the x first. You see, this is going to be the case about this one. So if you factor the denominator separately, this is x cubed minus x. You know that to factor it, you pull out the x. So that gives you x out, which is going to be x squared minus 1. And of course, x squared minus 1 is also factorable. So that gives you x times x minus 1 times x plus 1. You see, we get 3 factors. So our function is going to be, you see, this is the function, x plus 3 on the top. And we have x times x minus 1 times x plus 1 here. You see, you have 3 factors. The first factor would be 0 at 0, x. The second one would be 0 at 1. And the third one would be 0 at negative 1. So we are going to exclude 3 numbers over here. Okay, so don't miss it. It's very rare. But if it is going to be coming, so we are ready for it. So we have to exclude the 0, exclude the negative 1, exclude the 0, and exclude the 1. So you have 1, 2, 3, 4 partition. Okay, so the function is defined everywhere except at negative 1, 0, and 1. Okay, so this is it. So the d is going to be equal to, start with the negative infinity going to the negative 1, union with, okay, you go with the negative 1 and 0, and it's going to be union with 0 and 1. Okay, and the fourth one is going to be union with 1 and positive infinity. Okay, so this is going to be the domain of the function, but mostly is going to be of the three types that we talk about it already. Okay, any question? So that's the domain of these functions that we are going to have. Okay, so what else of the rational functions that we are going to be interested in for these numbers? Now, in order, eventually we would like to graph this function. Really, that's the main argument for this type of function. But when you want to graph it, remember the polynomials, the way we graph the polynomials for those numbers. Okay, let's see what is the question. No, you cannot use a bracket. Okay, so let me know if it's fast. Let me know. I solve that. You cannot use bracket. Okay, because if you use bracket means you believe that x is equal to 1. You know that x cannot be equal to the 0, x cannot be equal to 1, and x cannot be equal to -1. So you never use bracket, just parentheses only. Any question? So that is the domain of the function over here, okay? So this is the one that we did before for the domain. But there is something new about this type of function. Let's see if we can get get the preliminaries of that. And that's the end behavior of these functions. Remember end behavior for the polynomials? End behavior was when x goes to -infinity or the positive infinity. That was the end. The end behavior is when the value of the x getting, increasing without bound or decreases without bound. That's where we get that, that end behaviors. For the rational functions, the situation is going to be two-folded, if you like. So look at these functions. You are going to have two variables, x, one of them, y is the other one. Or we have the x and we have the f of x. Both of them can be infinity. You see, you can have the case that this x would be infinity or getting closer and closer to the infinity. And the case that the result of the fraction would be infinity over here. So we are going to investigate what would happen when one of these variables goes to positive infinity. The situation is going to be, we are going to have two cases. When x goes to infinity, that's the end behavior that we did before, remember? This is a polynomial. When x goes to infinity, we're just focusing on the leading term, which is x. We're focusing on the leading term, which is x cubed. So we can find the situation for the y by looking at this leading term. So if you simplify it, the result would be a number. So this is y. It would give you y equal to 2, y equal to 3. What type of line is this, y equal to 3 or y equal to 2? Any suggestion? What's the shape of line y equal to 2 if you want to graph it?
Horizontal.
Excellent, horizontal. So what's going to be the idea? The idea is going to be if you find the end, if you let x goes to infinity, if you like. You see, look at this one. The leading term on the top would be x. Down the bottom would be x cubed, if you like. If you simplify it, that gives you 1 over x. 1 over x means you get the whole on the top, infinity on the bottom. When x goes getting bigger and bigger, that gives you y equal to the 0, if you like. That line, if you change the x going to the infinity, and you get a fixed line like y equal to 2, y equal to 3, that horizontal line is called horizontal asymptote. So what does it mean? This means when x getting bigger and bigger, your graph eventually becomes like the straight line. That straight line would be that horizontal line, y equal to the 3. So that's why we call it, we call this one horizontal asymptote. This is very, not complicated, very detailed point or subjects that we usually discuss in calculus. We don't have it over here, but we are going to use these in behaviors to talk about it. So if x getting bigger and bigger and bigger, but the value of the y getting closer and closer to a fixed number, y equal to 5, y equal to 7, in that case, that y equal to the 5 or y equal to the 7 is called horizontal asymptote, because this is horizontal line. Okay, this is going to be horizontal asymptote. Sometimes you are going to have the other way around. The other way around is, you see, look at these numbers that we talk about it. We said, somebody asked, can I use bracket? I said, no, you can't use it. Let's use the bracket one. You see, let's use x equal to 1. If you put x equal to 1, what are you going to get here? The top would be what? 1 plus 3 would be 4. The number would be 0. 4 over 0. 4 over 0, you see 4 is a whole. If the denominator is getting smaller and smaller, the fraction getting bigger and bigger and bigger. Some people, they say 4 over 0 is infinity. You can accept that one. If 4 over 0 is going to be infinity, this means y is infinity. Y is infinity when x is equal to 1. In that case, that x equal to 1 is a vertical line. We say, oh, that is vertical asymptote. So there are two characteristics of these graphs, which is going to be interesting. And that is going to be the end behavior of this graph. One of them is going to be horizontal asymptote. The other one is going to be vertical one. I write the definition for you, but I'm not, we are not going to rush to make sure you understand this. It's very easy to find. Even in your book, they give you instruction, you memorize it and you get it. But it would be interesting, to exactly find what is going on. This is basically in behavior of a rational function. I write it down so that we have it, then we can talk about it a little bit tonight, and then we continue talk about it next time. Okay, let's get back. Any questions so far on this one? So we have a rational function. So far you should be able to find the domain of this function for us. 4 possibilities. Nice. The denominator cannot be 0. X equal to -3, take it out. When you take it out, make sure you use parentheses. You cannot use bracket. If you use bracket, this means you believe in -3. -3 make this one 0, which is impossible. Over here, we get x squared minus 4. We factor it first. It's going to be 0 at 2 places, so we take out these 2 numbers. Don't simplify. Over here, x squared plus 25 is never factorable. So we never get 0. So this function is defined everywhere. Okay, so 1, 2, 3 cases. The other 4, it's just for fun. You can have various formats. Now, what would happen if these x or y, one of them would be infinity? Okay, so these are the one that we are going to call it asymptotes. Okay, so what is going to be asymptotes? Okay, this is it, asymptotes. Asymptotes of a rational function, of the graph, or just a rational function, of a rational function. So as I told you, the asymptote would happen if you increase the x, if y getting to a fixed number, y equal to the 4, y equal to the 5, you say, oh, that's horizontal asymptote. You increase the y, if x getting closer and closer to a number, x equal to 5, x equal to the 7, or x equal to the 5, equals to 7 is a vertical asymptote. Okay, so I give a definition of both of them. This is it, at least the definition tonight. So if f of x, if you want me to slow down, just let me know. I just otherwise I go on. I assume that everything is fine. So if f of x is equal to, as usual, n of x d of x. Okay, if this is going to be a rational function, is a rational function. Okay, if this is going to be the case. Now the situation is number 1. I'm going to increase the x, getting the y, increase the y, getting the x. Okay, that's going to be 1. So the line, okay, the horizontal line, if you like, the line y equal to, the line y equal to, let's say, k, horizontal line, is going to be, is called a horizontal asymptote. Asymptote of the function or of the graph of the function f. Okay, function f, if, okay, if this is it, if f of x getting closer and closer to the k, whenever x goes to infinity. X can be a positive infinity or can be a negative infinity. Okay, you increase, it's the end behavior. It's the end behavior of this function. Okay, if x getting bigger and bigger, and you'll be able to find the f of x getting closer to the fixed number, in that case we say, oh, y equal to the k is going to be horizontal asymptote. And we find it just using the end behavior in a minute. Okay, that's a horizontal asymptote. The second one, the other way around. The line this time, x equal to the, let's say x equal to the h, is going to be just a vertical line. It's called, okay, it's called a vertical asymptote. A vertical asymptote, okay, is vertical asymptote of f of the function f, if the other way around. Okay, if x getting closer to the h, whenever, okay, whenever, okay, this is it, whenever y goes to infinity, that's 1. Okay, so this is going to be y goes to infinity. Okay, so if y getting bigger, one of them must be infinity to get the, to get these numbers. So this is going to be vertical asymptote. There's going to be a third case. It's going to be, a slant asymptote. We talk about it later, to get to know this one first, and then to get to the other parts. Okay, and now the question is how we're going to find it to get these two asymptotes. Okay, so let's just give you an example so that you can see what we are talking about. So look at this example. Look at this graph. Okay, look at this graph. You see, if you look at this graph over here, look at this one. So if you look at this function, this is going to be a positive infinity. Okay, and this is a negative infinity. Okay, let's give you this. This is going to be eventually the graph of the rational function over here. You see, in this case, as you can see, when x getting bigger and bigger and bigger, your graph is going to be getting, you know, closer and closer to this line. Look at this line. You see, this line is y equal to the 0. So when we say it's horizontal asymptote, this means your graph eventually becomes a line. It's like the horizontal line over here. You see, this graph, as we move on, x getting closer and closer to the positive infinity, the graph becomes a line. This is going to be the line that you're going to have. So this is the meaning of the horizontal asymptote. Horizontal asymptote is eventually your graph, if you like, to get these numbers. Okay, and the other one is going to be this one, the vertical one. You see, this is the vertical one. The vertical one is what? Is x equal to the 0. So this is going to be the other way around. And this means if, you know, if your y getting bigger and bigger and bigger, so in that case, the graph would becomes like a vertical line. We are going to find it, and we are going to graph it eventually. Then you are going to see it to get these numbers. Let me just give you the instruction, just one instruction to see how we are going to find the horizontal asymptote or the vertical one, and then we leave the rest. We check it again on okay, next week. So let's see what is going to be this, at least one of them. Okay, horizontal asymptote is, vertical asymptote is going to be easier. So finding asymptotes. Okay, finding asymptotes of this function, f of x equal to n of x on the top and the d of x down the bottom. Let's see how we're going to do it. Step 1. To find the domain of the function first. That is going to be a step 1, okay? Find the domain. Find the domain. Domain of the function. That is going to be a step 1. To get the domain of the function, you know that. You did the denominator equal to 0 and exclude those numbers. Next. Remember, I told you don't simplify. Now I'm going to tell you do it. When you find the domain, okay, if it's possible, okay, reduce, if you like, reduced. Okay, reduce the function, the fraction, if you like, the ratio or the function. The function by removing or factoring out, by removing any common factor, any common factor, okay, common factor of nx and the dx. So basically simplify the fraction, okay, basically simplify the rational, okay, basically simplify nx over d of x if it is possible, if it is possible. So in the following order, you find the domain first, and then if you get a chance, simplify it. Now go for the vertical asymptote. Very easy. Solve denominator equal to the 0 to find vertical asymptote. vertical asymptote. Asymptotes. Okay, that's going to be 1. Sorry, this is vertical asymptotes. Okay, very easy, but we have to simplify it first. The number is already factored it. You already factored it, okay? You let it equal to the 0, so that give you your, okay, your vertical asymptote. And part 4, this is a theorem for this one, but we are going to say that use and behavior. And behavior of polynomials in x and dx to find horizontal asymptote. There is a shortcut for this one. We talk about it later. That's it. This is how we're going to find those, okay, vertical or horizontal asymptotes. It's easy procedure when you are going to do it. There is only one that takes a little bit time, but for the rest, it would be easy to find. I'll just give you one example and we leave it for the next time. There are 3 examples only, and we give all the 3s as one question on your next test. You get 2 questions from the rational function, then we give you 1. Okay, are you ready? I'll give you an example next time. You see, it takes times. So I repeat this one again next time, and we give you example and we continue. Okay, this is the rational function, then we have to graph it. You need a full lecture to be able to do it. So we finish this one on Monday. I probably should post your practice test number 2 over the weekend. Okay, I will post that one for you. It's going to be test number 2, and there's going to be a take-home one. Okay, I think it's take-home 4 or 5. So give you enough time to be ready for your next test. Okay, I double check it. Maybe probably maybe on Wednesday. That's going to be one. But I check to see what's going to be the one. Okay, so I repeat this one next time. Don't worry about it. Any question? So get those rational polynomials that I talked about tonight. They are very easy. If you get practice, quickly you can find one factor and just do the rest. And then we take care of this rational function before your next test. Probably give you the test up to these sections. Okay, any question? So as I told you, just check your quiz number 2. If you want to add the numbers, remember there were 6 questions. You are going to add 5 only. So add those numbers. Anything is missing, just let me know. That's one. The other one is I will add all the, I think I've already added all the assignments. All your assignment, take on one. If anything missing, send me an email. Then I'll check it for you. Okay, just make sure before they get the next test, all these points are already given to you. So let me get a new take on one and we can continue. We are not going to collect any assignment on the day of the test, you know that. So the next test is good. This assignment would be in something like 4 weeks times. Okay, that's it for tonight. Any question? So have a good night and have a good weekend.
Thank you.
Take care. Take care. See you next week. Bye-bye.
Bye.
Bye.